Yeah, I'm
And
so it's
all right, guys, and we are live. Welcome, Brian Keating to the podcast. Great to have you.
Great to be here, Rick. Thanks for having me on.
Great. Well, you've seen Brian both on Joe Rogan and Lex Fridman very frequently, very recently, I think. Brian's the distinguished professor of physics and a public speaker, inventor. He does everything. He's an expert in the study of the universe's oldest light, CMB, cosmic microwave background, which I think we're going to get into here in a second. Brian's a writer and podcast. You've seen him stuff all over the place, very prolific. And he's also the best-selling author of what Amazon calls one of the best nonfiction books of all time. Welcome, Brian.
Thanks so much. Yeah, it's great to be here.
Great. And we are hoping to discuss today, I'm getting an echo here. We're hoping to discuss today a little bit about your writing process, your creative process, and then also sort of the nature of genius within the scientific sphere. But I want to get started by talking a little bit about the idea of curiosity in your book, Into the Possible, and not even losing the Nobel Prize. Both fantastic readers, I highly recommend, and we'll link to below. You really take this childlike curiosity very seriously, especially as you open up about your own childhood, the nature of looking at the telescope and what it meant to you in your life there. And I want to start off by getting your take on this quote from C.S. Lewis in his book, The Abolition of Man. He says that the serious magical endeavor and the serious scientific endeavor, Brian, are twins. One was sickly and died, the other strong and throve, but they were twins. They were born out of the same impulse. And so, Brian, could you tell us a little bit about, from your perspective, the relationship between this kind of childlike curiosity, this magic, and science itself, especially for you as a kid, and what it means to you today?
Yeah, I often think about that kind of quote, or that idea that science is, pursued by scientists who are childlike. And that's actually very close to my experience, that, scientists are like children. We're curious, we're passionate, we are intense, we're focused, and we get so wrapped up in what we're doing. But also, like children, we don't play well with others. We love to get credit. We're jealous, we're petty, we don't share our toys. And so nothing is really a single-edged sword. Everything comes with kind of blessings and curses. And I think, the challenge is to kind of not grow out of the childlike curiosity, passion, and wonder, but do grow out of some of the lesser, more base characteristics that children are typified by.
Yeah, and you call curiosity, I believe you call it the secret sauce, that it's so important in scientific and really any exploratory work, and that it leads to resilience somehow. How does that work? How does curiosity make science and sort of the exploratory arts more resilient?
Well, I think, passion can kind of only get you so far. I think people advise you to, follow your passion and, everything will go your way. But in reality, very few people make a living out of something that they're passionate about. I mean, if it were me, it would be ice cream tasting or something like that. And in fact, it's quite hard to become a scientist and become a professor like I am. But the challenge that, I think is worth overcoming, it can only really be overcome if you have more than just kind of temporary willpower. You listen to people like Joe Rogan or Jocko Willink or people, David Goggins, they'll talk about willpower is depletable. You only have so much willpower, but if you really change your habits, change your mindset, and so forth, then it becomes sustainable. Well, I feel the same way about passion. You might be really passionate and think about the goals of, the outcome, the final product of being a scientist, maybe getting attention, maybe getting, credit, and maybe really truly discovering something new. But there are no real ways to sustain that passion other than to have just in unwavering scientific curiosity. And so I find, it's necessary to have passion, but it's not sufficient. You need to have something that will sustain you through the very challenging times, the boring times, the mundane times, the competitive times. These are all traits that require more than just pure passion.
What do you think the relationship between passion, curiosity, and genius? Like, I'm talking about global, earth-shattering genius, things like people like Newton, Galileo, and Einstein. Did they rely on curiosity and passion as much as maybe scientists of today need to, that are not, world-changing genius?
Well, I think certainly they did. I don't think there's such thing as a scientist who's successful that's not incredibly curious. But they were also passionate. That's why I'm saying you need both. You need to have really this true kind of conviction that the struggle's worth it. But that's also not enough. You also need to have this enduring kind of unyielding dedication to the craft of being a scientist, like being an actor. Like everyone wants to be an actor. They come here to Southern California, come to Hollywood, and they want to be an actor, passionate about it. But do they have the kind of fortitude to withstand all the things that aren't part of that craft? And that makes it part of the craft to kind of endure and be resilient and make up for the times when it's not going to be all award shows and so forth, and being in TMZ or whatever these people aspire to be. So the trait that I see in common, to answer your question, is really twofold. There's really two traits that you need to be a good scientist, and one is to have have kind of supernatural confidence that you can do what you want to set out to do, because otherwise you'll just be kind of lost. Nature doesn't reveal her secrets. They're quite deeply hidden, and most of the easy, quote unquote, easy stuff has been discovered decades and centuries in some cases earlier. So you need to kind of have this supernatural confidence that you can achieve greatness and that you can do what others haven't been able to do. And that's the goal of science, is not to only confirm what other people have done. That's important, but to actually understand and have conviction that you're going to do something new that no one's ever done before. That's a requirement to get a PhD, really, is you have to do novel research that no one on earth has ever done before. And then secondly, the other counterbalancing trait is to have humility, and to know that you shouldn't be overconfident, and that you are flawed, and that you will succumb to different biases and have different challenges, I would say, in your pursuit, that you're not going to be able to eventually do everything and know everything, because science is infinite. You may have heard of finite games, infinite games. A finite game is chess. There's a winner, there's a loser. There are rules of the game. The game object of the game is to end the game by you winning. But science isn't really like that. There's no winning science. There's no person who knows all of science or discovered all of science. Not even the greatest geniuses that you mentioned. So the challenge is dealing with the infinite game of science, but knowing you have to play a whole bunch of finite games along the way. Get into college, get into graduate school, get your PhD, get a professorship, get into tenure, all these things, get research funding. And to have that as a notion of how we do science, it's difficult to balance those two conflicting traits of confidence and humility. But the best scientists do that, and don't let the overbearing nature of how challenging science is crush their spirit, but also don't get too overwhelmed by their own greatness, that they have an inability to actually get things done because they think they know the answers to everything already.
So I think about the entertainment scientists. That's how I phrase it. The Michio Kakus, the Neil deGrasse Tysons, people of that fare that really are putting all their eggs in the MTV basket, as Will Ferrell would say. I think you have connections to San Diego. I know he's rolling around there on occasion. This idea that I can be sort of an all-inclusive scientist. I know Michio has some other things specifically in string theory, that sort of area there. But what is the role of science in dealing with the public, and how much is a good scientist spending, I guess, effort on trying to communicate to the outside world what exactly they're doing?
It's a challenge, because not everyone can do, science, and not everyone can communicate science. And the Venn diagram of people that can do science and also communicate science is even smaller. Any restriction makes the subset of people even smaller. And I think, the challenge is when you feel like it is your job or it's not your job to do either the communication or the distillation in terms of what the public can understand. And what I always say is I think it's actually almost a moral obligation that scientists have to the public, who pay our salaries, whose taxes fund our research. And every scientist I know would do what he or she does for free. They don't require funding for it. They don't require, to have the passion. And we're doing what we were doing as kids. And we certainly didn't get paid when I was 10 years old and got my first telescope. And so we're doing what we would do for free. And so the fact that we get to get paid for it is incredibly generous of the taxpayer. And for us to say the taxpayer is basically not our boss, but is responsible for our funding. So kind of like a boss to say, well, no, I'm not responsible for explaining things to you. You can't understand what I do. And therefore, I'm not going to take the time to communicate it to you. And a lot of my colleagues in science will say, no, that's not fair. Scientists should do science, and communicators like Michio Kaku or, Neil deGrasse Tyson, who aren't doing active research, they should, they were scientists, they have done stuff, but they're not doing it now as much. They should be the ones that rely. Then you get this really distorted message of who is a scientist and, who can do the process of science. And I think that that's an incredible, kind of bad message to send to young people that, you can either do science or you can communicate science, pick one. And there are a few that do it, or very few, but oftentimes they'll say it's not easy for me to do it. I'm not good at it. I'm better, solving equations, or I'm better doing laboratory work and building telescopes. And I'll say, oh yeah, I know that. You were born knowing quantum field theory and understanding the nucleus of the atom and quantum mechanics. They'll say, no, I had to study it. Well, okay, so you studied it. Why did you study it? Because it was important to me. Oh, so what you're saying is you could learn how to communicate to the public, but it's not that important to you. And then I feel like, that they've kind of lost the battle at that point. It is our responsibility to do it, to communicate to the public, and we can all get better at it. And the ultimate benefit is that it becomes an asset to the scientists to be able to explain things to people who aren't experts, both for their career and for the blossoming and flourishing of science in general. We need more scientists to communicate how awesome science is to the general public. And it shouldn't be so hard, because in fact, nature is the ultimate, Oscar-winning script. There's nothing more interesting than or magical about science. A famous quote by Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic. So we get to be magicians. And then we're saying, oh, we don't want to do that. We don't want to explain how the tricks are done. Okay, well, fine. But just admit that you're not fulfilling the entire, entitlement that you are owed, to do, and that you have a tacit contract with the general public who pay you. Because eventually maybe they'll stop. And then we'll see how happy you are doing not science and not communication.
Well, that's so funny. So you had this other idea about the how great science looks like magic. You also have this idea that I think Wigner put forth a number of years ago in his famed paper, The Unreasonable Effectiveness of Mathematics and Science, something to that degree there, where he talks about this uncanny translation of science into mathematics. How it's explainable in that. Where do you see the relationship between mathematics and science?
So yeah, the quote by Wigner is about, it's called the unreasonable effectiveness of mathematics in the physical sciences. And it's kind of highlighting the fact that science is somehow distinct from mathematics. I mean, we take for granted that math, you have to be good at math to do science, but actually, if you look at math, like pure math, there's nothing scientific about it. It's purely intellectual. It's purely conceptual. It's the properties of these completely immaterial and purely psychological constructs, like numbers. Like there is no such thing as a triangle. You cannot give me a triangle. You cannot make a triangle that's a perfect triangle, 3 zero-dimensional points, arranged in some angles. And so for this reason, I think it's incredibly confusing to people that actually math doesn't necessarily have anything to do with science. And another, kind of aspect that is pointed out in this famous essay by Eugene Wigner is, when you ask, well, what's the, bell curve look like for people's heights in a population? Or, what's the average, 7-year-old height? You get a bell curve distribution where there's an average and there's an upper bound, that's kind of soft. You have some, 6 foot tall 7-year-olds, I guess, and, a couple of much shorter 7-year-olds. But then you have some average where the vast majority lie in there. Well, that distribution, the normal distribution, the bell curve, it's called a Gaussian distribution in mathematics. And that Gaussian distribution has within it the number pi. And what does pi have to do with anything? And the number that expresses the ratio of a circle's circumference to its diameter. Like, what does that have to do with like the height of 7-year-olds? Well, it turns out to be very closely related to the properties of the function that describes the physical set of 7-year-olds. So, but that's a surprise, and it's something that's very useful, where you don't see it as as much usefulness, say, in philosophy or logic and in the laws of quantum mechanics, but you see mathematics everywhere in every branch of physics. So it is quite surprising, and I think it's quite beautiful. And the question I always think about is, does everything in math have some manifestation in physics? Like angles, geometry does, the properties of integers and numbers do, and pi does. But does every possible conceivable mathematical structure parlay itself into some physical thing that my colleagues and I could measure? It's an open question. I actually don't know the answer to it, but it's fascinating to think about.
Yeah. And I think it's something like string theory. If you're working, let's say in 10 dimensions there, and if one of the requirements for something to be a science has to be that it has to be disprovable or falsifiable, it's really hard to falsify 10 dimensions without just using pure mathematics. And so things like that are string theory, just for instance, is that a real science? Is that more of a mathematical endeavor?
Well, there are some that say it's both, and there are some that say it's neither, and everywhere in between. There are people that say it's part of legitimate science. It's well justified by sort of this reductionist concept that I should explain. That for people that aren't familiar, string theory asserts that the particles that we had long time thought were indivisible, fundamental, elementary. They cannot be divided into smaller and smaller chunks the way that ordinary matter, a chunk of rock, could be chopped up into smaller rocks, eventually molecules, eventually atoms. The atoms contain within them protons, which can be broken up into things called quarks. And the question was, are quarks broken up into other things? And for many years, people thought no. But an interesting and speculative idea came about in the 60s that perhaps each quark was a manifestation of a vibration of a concept called a string. And the string behaved in a calculatable way, and it had certain properties which then were possible to then bring together other phenomena like the property of gravity and unify that with the property of quantum mechanics. And we weren't really sure if that was possible to do necessarily. So I think it's an open question whether or not it's proper, in terms of will it achieve its goals. The problem is that it doesn't seem to make predictions that can be tested. And the job of a scientist is not to prove something right, it's to prove something wrong, and prove as much wrong as possible. And then what's left has a possibility of being closest to the truth. But we as scientists don't prove things. That's a difference between science and math. That mathematicians do prove things like 1 + 1 = 2, but they do so in a very, very, obtuse and very complicated way it takes to prove such an assertion, but it's possible to prove it in a way that's irrefutable. Whereas something in physics, I could say, there are purple unicorns on top of the North Pole of Saturn, and I could go there and observe that there are no purple unicorns there, and that destroys some theory that had that as its prediction. But at least there's a prediction, so it can be disproven and falsified in the language of philosophy, Karl Popper and others. But the concept of string theory doesn't really seem to make predictions. It makes kind of assertions about the nature of reality, but they can't be tested at the anywhere close to the type of technology that we have today. So I think that's it's an open question whether or not it will actually be accurately represented by are these microscopic strings really representative of the ultimate building blocks of matter? And that's an open question.
Yeah, that's fantastic. The idea, and I'm a business guy, so I'm sitting at a desk all day long. So this is fascinates me here. So the idea that string theory is maybe a kind of a theory of the interoperability of various domains, akin to maybe the next evolution from relative theory to general theory, and so forth. Is that the right way to think of it for us sort of common people? Is it a continuation of Einstein's work, or is it something very, very different than that?
It is. It's related to Einstein's, unfinished dream, which was to connect the laws of the largest scales of physics, which is the law of gravity that describes how the universe itself is composed and its structure on the largest possible scales, ranging, out to the very beginning of our universe. And the Big Bang Theory is intimately connected to Einstein's theory of general relativity, all the way down to the scales of our solar system and planets and navigating to, the moon and Mars and so forth. Those are all related to the laws of gravity, to make those sorts of excursions into space. And then the question of the ultra small, the quantum nature of reality, the building blocks of nature, the protons and neutrons and electrons, and they behave via a very different set of laws called quantum mechanics. And that type of behavior is not possible to really combine with the laws of gravity. They don't seem to behave properly. Gravity doesn't behave the way that the other laws of physics, the other laws of nature behave on ultra microscopic scales. So when you're at a level of size scale of, fractions of a billionth of a billionth of a meter, those scales are purely quantum mechanical in nature. And the question is, can gravity be made to be quantum mechanical? And it's not really clear if that's possible or not. So what Einstein tried to do is come up with a way to unify the laws of gravity with the laws of quantum mechanics. And he died not having accomplished that. So a lot of people venerate Einstein, and I do too, and they seek to do what even Einstein couldn't do. And for good reason, it would be an incredible accomplishment. But the challenge is we're not really sure if it's possible to combine gravity and quantum mechanics. They may just be fundamentally separated. The good news is that, well, it only really comes into play on the scale of the ultra small, perhaps only in the very first instances of our universe's history after the Big Bang, in which case gravity and quantum mechanics would have to be combined. And the other place that gravity and quantum mechanics seem to be intermingled is in the center of black holes. What's called a singularity of a black hole is a region of space-time where we think the laws of gravity and the laws of quantum mechanics would have to be reconciled or combined. And for that reason, we're also kind of immune to anything that happens at the center of a black hole, excluded from any effects of it via what's called the event horizon. So in both these instances, 14 billion years ago nearly, and at the center of a black hole, we do believe that quantum mechanics and gravity could be related. But if they're not, there's not necessarily an indefinite prison cell that we're sentenced to that we wouldn't be able to recover from. So I think that this is, kind of an interesting turn of events, but it's not necessarily mandatory that gravity and quantum mechanics be unified the way that Einstein thought that they somehow must be.
Yeah, and I think that I saw an article fairly recently, and I think I guess space.com or something more like that, talking about how there's been a discovery of Einstein's prediction that there would be matter at the periphery of black holes that then sort of waterfalls down into the black holes at speeds very close to the speed of light. But it seemed to me like Niels Bohr's discoveries in the early kind of 1920-ish type of time frame, where electrons were really moving around, not like faster than speed. Like, I guess the location is not approximate to speed or anything like it. Just random placement of these electrons. If those are two different things, two different spectrums, even if you could get the matter that falls into these black holes at the speed of light, it wouldn't be as fast as what Niels Bohr's instantaneous synchronization of the electrons. Are those two different scopes, two different magnitudes of speed and placement, or are those just two totally different domains?
I'm not 100% sure the question. I'm not familiar with those terms. It might be you're not using the terms properly, but
that's exactly what it is. I'm sure that's what it is.
I'm not really clear about that. I'm not familiar with that. If that's indeed the case.
But the electrons, they're in two different places at the same time, or what's the proper way of understanding that compared to the concept of speed?
Oh, yeah. So there's something called the Heisenberg uncertainty principle. Is that what you're talking about?
I think so.
It's incompatible to measure both the both the position and the velocity of a particle at the quantum scale. So these are things like electrons, or even quarks, or subatomic particles, or photons even. So the question of simultaneously being able to measure it, it's actually not that surprising when we look at things like, imagine yourself inside of a completely dark room, and I tell you there's a ping pong ball rolling around the floor. So it's on the floor of the room, but it's totally dark. You can't see it. And I'm asking you to tell me exactly where it is right now and how fast it's moving. And so you would set out and you'd wander around and you try to find this object, the ping pong ball rolling around. And then maybe you luckily come upon it and you stop it, right? So you stop it, you know exactly where it is in the room. Now you can turn on the lights or whatever. And then you know exactly where it is, and you know nothing about how fast it's moving. You've caused it to collapse and be in the exact position, and in so doing, you've forced its velocity to be zero. So that's a challenge. That's a big challenge. And I think it's incredibly, interesting, but it's not so surprising when I use that example. And then you could say, well, what if you didn't have to use your hand to stop the ping pong ball? Right? What could you do differently? Well, you could turn on the lights, and then then you could both measure where it is and how fast it's going, using a camera, say, and making a movie of it. But to do that requires that there's particles of light, and those particles of light are bouncing off the ping pong ball. Well, the ping pong ball weighs, hundreds of grams or something like that. But when you talk about subatomic particles, they weigh a billion times less than that. So a photon to them is like trying to see where the ping pong ball is using a cannonball. So that would obviously change the result of the measurement very, very greatly. So the Heisenberg uncertainty principle is an expression of how the incompatibility of measuring something's position and momentum, which means that effectively, if you know something perfectly well, you cannot know another complementary observable about it with any degree of precision whatsoever. And that came to become one of the great paradoxes of quantum physics that's not present in the example I used in so-called classical physics, where you could do a simultaneous measurement of position and velocity.
Yeah, I think Bohr called that a paradox. What's the opposite of a truth? It's a higher, more ultimate truth. Something to that degree, and that is perplexing. So is there an observer issue with it? Like, does the observer have any play with that?
Yes. So the observer is the one who's doing a measurement. When you do a measurement, that does force the quantum state or the object into one specific state that is not possible to really change it or modify it in any way. So yes, it does sort of force that place to be in a certain configuration.
Okay. It seemed in your books that there is a lot of affinity towards the man Galileo. That there's a lot of respect, a lot of sort of backgrounding of your life in the story of Galileo and Newton to a certain degree, but Galileo seems to be sort of preeminent there. What does Galileo mean to you, and why should people take sort of up a new cause of learning about Galileo, the man, and his work?
Well, he's really the first scientist in the modern sense that we use the word scientist, and someone that is using the scientific method of, creating a hypothesis and then drawing inferences for what you would see in that hypothesis being correct, figuring out ways to disprove himself wrong. And that's a vital part of science, is self-correction. And then iterating and doing so using the tools of science, modified versions of this. Telescope is a very simple but extremely powerful tool, and that's what he used to create the very first scientific hypotheses in the modern age, 414 years ago, when he postulated that when he saw the little stars that seemed to surround the planet Jupiter, that those were actually moons. And those moons were orbiting around Jupiter, which we take for granted now, just as we take for granted the Earth's moon goes around the Earth. But back then, the predominant paradigm was that everything orbited around the Earth. So how could you have, including the sun and including Jupiter itself? So in this case, it was clear the moons were not orbiting around the Earth, they were orbiting around Jupiter. So that completely didn't prove that the Earth is not the center. It didn't prove that the sun is the center of the universe, as many people, which is the truth, not the truth. I mean, the sun is not the center of even our solar system, let alone the universe. But back then, they considered the universe to be the whole solar system. So the paradigm that Galileo was trying to prove or substantiate or validate was that the Earth was not the center of the solar system. So he did consider that and did prove that effectively via this observation and hypothesis that no, actually Jupiter's kind of like a miniature solar system in itself. And that meant that we couldn't really substantiate the scientific method of believing that the Earth was the center of the universe, but people believed that for thousands of years. And so what Galileo did is show that evidence, a fact, a brutal fact, can destroy a beautiful theory. And the theory of the Earth being the center, it sure looks like that. I mean, if you ask a normal person in your audience to prove, that the Earth is not the center of the solar system, when it sure looks like that, with the sun looks like it goes around the Earth, how would you do that? And I bet 90% of the audience couldn't do it, even as brilliant as they are. And that's because we don't really teach these things. We don't really understand. But back then, imagine how revolutionary it was, and that Galileo had the courage to do that. He also made incredible blunders and mistakes. And because of those mistakes and the ability to kind of have some humility, as I said at the beginning, he balanced that great courage, confidence, chutzpah, almost arrogance, but he balanced it with the notion that he could be wrong. And he was wrong many, many times, including about some of the evidence that he thought was the most, convincing, that proved that the Earth was orbiting the sun. He was actually wrong about. And that's an interesting kind of topic in the scientific history of the Western world. But because he had that balanced idea between being confident and being humble, and because he was so eloquent, he was such a beautiful writer, his prose and his literary devices, he wrote books in dialogue or trialogue format that are just so readable, and his writing is so beautiful. It's actually almost poetic, but it's even more than that, because he's teaching you science using a vector of beautiful writing. And I had the honor of not translating, but taking translation from a written word only to an audiobook of Galileo's dialogue book. So I think that was an incredible thrill for me to be able to do. And I'm honored to have done that. About 3 years ago, I made the first ever audiobook. You can get it on Amazon. It's called The Dialogue on the Two World Systems. And, I share a co-authorship with Galileo. So it's pretty cool.
I'm sure he was pumped about that as you guys went on the book tour together. I'm sure that was very exciting.
I do have him here. He's right here right now. I've got this wonderful version of Galileo right there. And attached to him is a meteorite. So I want to extend an offer to your audience. If you go to my mailing list, briankeating.com/list, and you join my mailing list, every month I send out one of these beautiful meteorites to one of the lucky subscriber each month. Unless you have a .edu email address, and then I guarantee I'll send you one of them if you live in the United States. So briankeating.com/list is where to get your own chunk of the 4 billion-year-old primordial solar system, long before even the formation of the Earth. This fragment of this meteorite, which would later hit the Earth in Argentina about 6,000 years ago. And I send a lot of information about how to view meteor showers. There's one coming up in about 2-3 weeks called the Perseid meteor shower. So I'll tell you all about that at my website, briankeating.com/list.
Yeah, we'll definitely link to that. So I want to get into CMB, but now that you're on the newsletter topic as well, walk me through your content creation process, because you are so prolific between the books, between the audio project, your podcasting, your guesting, then obviously your newsletter business as well. Walk me through kind of what your average week looks like. What does the team look like? Because you're pushing out a lot of content.
Yeah, I have a great team called Legacy Media, and they take basically all the content that I produce. They'll take this video, they'll probably make it into some clips eventually, and put a link to your channel on it. And but typically I really make 2 different types of videos of my own, and then I appear on podcasts like you and Joe Rogan and Lex Friedman and Piers Morgan and Jordan Peterson, etc. And those are always really fun because I get to, introduce my research and my thinking to a wider audience. So some of the issues come down to one or two different types of videos. Either I'm explaining something, the invention of the telescope, or some cool new discovery in the cosmic microwave background, or a claim discovery about some new technology or superconductor. I call those deep dives, solo episodes where I really try to explain it in a way that anybody can understand if they're curious. Again, that key ingredient, the thing that without which you can't accomplish anything, that trait of curiosity really comes into play, that they can follow it. And I provide references and stuff, but if they're really interested, I can go deep, and there's even more follow-ups and citations and stuff that people can dig into if they're interested. Then there is a type of video where I do an interview with an author. So I'll have authors usually, and this is how the podcast really started back in 2020 during COVID. There was basically no authors were doing book tours, and that included science authors. And I'd always gotten into science because I read books by great scientists, from Carl Sagan, Stephen Hawking, and Isaac Asimov, my favorite, and Galileo. And so I love authors. And when they were canceled and their book tours were canceled, I also had been on a book tour for my first book, losing the Nobel Prize. I got on a lot of book tours for that and really enjoyed that experience. And I felt kind of depressed for my colleagues and friends that couldn't go on and do interviews in person. So the next best thing was to do just like what you and I are doing. So I'd get their book from their publisher, and then I was able to get some really high profile, big name authors and businessmen and women and scientists and astronauts and just really cool individuals, the highest performers. And, it helps to be at a top university and to have a nice title along with it. But yeah, in terms of what the origin of that was, I was able to get a stream of content going back 4 years now. And so I'm able to, turn some of the old ones into, part 1, 2, 3, and kind of divide up into different topics. I talk about consciousness in the brain, or artificial intelligence and cosmology. And I talk about the origin of life. I talk about aliens, and all these different topics. And so now I've got, dozens of videos in each one of those buckets, and make playlists for those, and people get really interested in it. And I'm still now, thanks to having nearly over 271,000 YouTube subscribers and another 80,000 on audio, I can get pretty big name authors. I'm supposed to have a very, very huge name in the alien space coming on hopefully soon. I won't say who it is yet. I recently talked to Richard Dawkins, who's the godfather of atheism, basically, and he invented the term meme and the concept of the selfish gene and so forth. So I had him on 2 parts for a new book that he has. So I've just gotten kind of benefit of the content rich get content richer, and I'm able to kind of leverage that and get more and more cool and interesting people on the podcast.
Oh, I love that. I love that. So CMB. CMB, I think, helps us understand the origin of the universe. And I think that's a little bit about what your work was in your book, Losing the Nobel Prize, which is just fascinating. What is CMB? Why should we care about it? And what usefulness is it? Like, is it going to be helpful for you in your conversation with Dawkins? That sort of thing. Give us kind of a briefing about that for
yeah. No. So the CMB stands for Cosmic Microwave Background Radiation. It was discovered in 1965, and it was discovered by accident, and they weren't looking for it. They kind of found it, and then the interpretation of it became that it was the leftover heat from the origin of the universe. So in some sense, it's the oldest light there is in the universe. It's the oldest, and it's not visible light. It's called microwave, which means you can't see it. It's in the same wavelength range, ranging from the frequencies that your oven uses. And so what it traces is really an incredible amount. Just as humans primarily interact with the world via our eyesight, and our eyes get so much emphasis in our brain, and so much of our brain is dedicated to processing visual information, there's incredible amount of information encoded in the oldest light in the universe, which is this cosmic microwave background. So background means it comes in all directions. Cosmic means that it's from the origin of the universe, and microwave is the wavelength range that it's in. which is slightly shorter wavelengths than radio waves, like Wi-Fi, and much longer than visible light that we see each other with. So its discovery really marked a transition from an earlier phase of cosmology where astronomy and origins of the universe, it really wasn't taken seriously because there was nothing quantitative about it. It was kind of like, oh, there's some galaxies, they seem to be moving away with some speed, and yeah, we can measure the speed of the galaxies, but to have an actual leftover from the Big Bang itself that we can see any day of the year, any time of the year, all day long, that became such a powerful resource for understanding that the early universe was a fusion reactor, that it was creating these collisions of very, very high energies, resulting in the production of the elements in the periodic table, and then the very first atoms that formed. So an atom is the nucleus of an element, plus some electrons that surround it. That process couldn't take place for about 400,000 years after the Big Bang, and then that took a that actually took the notion to be much more precise, that we could actually study the universe quantitatively. So yeah, does that answer your question of why it's important?
Yeah. Very, very, very helpful. Okay, so we got about 5 minutes left. I want to ask you sort of some fun questions, Brian. So the first thing, and obviously, as everyone knows, more than Galileo, there's only one person in the whole world that you respect more. That's Candace Owens. What are sort of your off the cuff reaction when you see people like her and me making scientific statements and trying to have an intellectual conversation with the real scientists? Is it frustrating?
No, it's actually, I mean, it's frustrating when people deny the real work of true scientists that are working hard to unravel the mysteries of the universe at very low pay and and often in obscurity for decades at a time. And then someone can just come up and invalidate it and say, the moon landing never happened, or the Earth might not be round, or NASA and science is pagan, as they use their laptops communicating over wireless internet that was actually enabled by people that did discover the microwave background at Bell Laboratories in the early 1960s. So
wow,
it is sort of offensive to think that those kind of things catch on so much. And conversations I've had with Piers Morgan and others like my friend Eric Weinstein, the question is, well, how seriously do you take people that are narrative or heterodox thinkers, people like Terrence Howard and others that aren't experts, but as long as they're not too conspiratorial, or and some conspiracies turn out to be right. I mean, you and I had a conspiracy to record this podcast and have it get 1 million views, and it will, right? But yes. So it's not only a pejorative term, but in the context of undermining faith and things like, she doesn't, I believe, according to Piers Morgan, even have any vaccines for her kids. Those types of people, have a lot of explaining to do of why that's actually the case. They want to rely on things and generate confusion and so forth, but a lot of it is to generate outrage, and because outrage is what causes engagement. So I do kind of feel like they should be listened to, but they should be dismissed where appropriate with extreme discretion. We should be able to, as a scientist, again, part of our obligation as scientists is to refute things that are nonsensical. Now, we can't spend all of our time doing it, because it's way easier to create a theory that something never happened and then say that to disprove that this thing is a conspiracy and then actually did happen. To disprove the conspiracy hoax model is a lot of work, and I'd rather be studying the Big Bang, to be honest with you. So I have to balance it. Sometimes it's worth the time to do it, and sometimes it's an exercise in futility. Part of what I do, and people, when they disagree, oh no, Candace can say whatever she wants, and you're just like a shill for big NASA and big cosmology, and we shouldn't listen to scientists. They have as much ignorance as anybody else, and it's not really true. If we're subject matter experts, if we've gone through the process of obtaining and dedicating our lives to it, then it's kind of shameful to accuse us of having these ulterior motives, especially when they make no sense. I mean, I support vaccines for, my kids have had vaccines, and I've had vaccines myself. And the question of, well, so am I getting paid by Pfizer? I'm a cosmologist. Like, that's not how it works. I think it would be more damaging to Pfizer if I were a cosmologist endorsing some vaccine. But the bottom line is, it's much easier for disinformation and confusion to be sown and spread around than it is to actually refute it and teach, kind of the good science that should be maintained.
Yeah. So funny story. A little while back, I was in a private meeting with President Trump. No matter what you think about him, and so there were 9 of us in the room. 9 of us in the room, and most of the people there were very well-known people. One of the people in the room, she owned a professional sports team, actually 2. She went on a rant about the vaccines, and after about 3 or 4 minutes, he stopped her and said, "You realize the vaccines happened under my administration, right?"
Yeah, right. Yeah, people don't want to admit that. And also,
wrong room.
Yeah, simultaneously, people don't want to admit that they suppressed the vaccine from coming out because Trump created it, or because it was created under warp speed, which he was responsible for. In other words, I've had very staunch Democrats that hate Trump or never Trump Republicans. I've had people like Sam Harris on my podcast, hates Trump, and but they support vaccines. So it goes both ways, right? The Republicans who are, condemning it and saying you're a fool or a shill in the case of a scientist, they also don't, have answers to the question of, well, why did these people support the vaccine, but not support the person who caused it to come about in the first place? So these are all people have cognitive dissonance and biases, and it's just a matter of being able to sort through with some degree of accuracy what incentives people have for saying the things that they say to you.
Okay. Yeah. Okay. Super quick fire. There were 3 names that caught my attention in your acknowledgments. How did you meet them? And maybe a word that we wouldn't know about him, maybe some sort of characteristic about him. Eric Weinstein that you mentioned a second ago.
Yeah. So Eric's been a friend. He's a mathematician, but he's decided to dedicate his life to physics and understanding possible new theories of everything. He's a theoretical inclined person. He's not an experimentalist like me. And so, the judge of a theory is an experiment. So how do you prove an experiment, or how do you test, prove meaning test, not improve meaning verify or validate. So you do an experiment. So what predictions does his model make that could be tested by experiments such as mine or my colleagues or my competitors? And those are the kinds of things that engage me about his ideas, that he's thinking so broadly and so diligently about ways to perhaps make the world better, perhaps, save us from ourselves and back up the planet, rather than taking some chemical powered rocket to Mars. Well, what happens if the sun, becomes a red giant in a few billion years rather, keep paying your taxes out there, Rick. But the point is, really getting far away from Earth could require changing and understanding Einstein's equations in a way that we and Einstein were never able to do. So I like big thinkers like that. And so that's part of my, connection with Eric Weinstein.
Roger Penrose.
So Roger's one of my long-term guests. I had him on years before he won the Nobel Prize. He's an incredibly original thinker. He has created new kind of paradigms and everything from our understanding of black holes, which is what he won the Nobel Prize for. He has ideas about the origin of the universe and how it did not unfold the way that most of us think that it did. But I like the kind of iconoclastic ideas. He's also thought very deeply about consciousness, the brain, and how conscious ideas and thoughts manifest themselves in our mind, and done experimental collaborations to determine that. So he's just an interesting polymath that can do millions of different things. And I find his ideas fascinating. And I know I'm not alone, even though, when I disagree with him, he's a gentleman, and we can always, debate and come to some kind of understanding of where he might be wrong, where I might be wrong. And I love that idea. And also his book was the first book that I ever read as a young person in high school. It's called The Emperor's New Mind. And that was about computers and consciousness and all sorts of really cool stuff that I never understood until much later in my life. So don't get discouraged if you're reading my books and you don't understand them at first.
Like, hey, last one. Dennis Prager.
So Dennis, I've known for 7 or 8 years. I'm Jewish. He's Jewish. He wrote many great commentaries on the Torah and the Old Testament that I find fascinating. And he's a very deep thinker. He's had me on his radio show many times to discuss the big picture. It's always called the ultimate issues hour that I come on. I talk about the James Webb Space Telescope. And, I always say I love, he's obviously very strict Republican, conservative, but, I always say I love cosmology or astronomy because there's no like Republican constellation or Democratic asteroid or, whatever, or the eclipse is an independent party, so it's a safe zone. I think human beings have too much politics, especially now. I mean, it's crazy how much politics just overwhelms us. And for that reason, I think it's important to get a break from politics. And part of the reason is to go on shows and talk to people that might have a different, biblical only approach, and really talk to them and see, if I can be of use to their audience and educating them about the most interesting subject that I could possibly ever imagine, which is our universe and the many wonders within it.
Great. That's a great way to end. Brian, thanks so much. And of course, what we're all hoping for is this grand utopia where there's no more politics. We all get behind the same sort of work, which obviously is going to happen when your former Senator Kamala and your Governor Newsom that have made California itself a paradise, especially downtown San Diego, come and rescue the entire world from all of our troubles with their competency and
from your lips to their ears. Thank you, Rick. Thank you so much.
Yes. Yes. Well, thanks so much for having us. We're going to link to everything below. Go pick up Into the Possible and Losing the Nobel Prize. Brian, thanks so much for your time. Great being with you.
Thank you. It's such a pleasure, Rick. Have a great day. Have a great weekend. Bye-bye.
All right. Thanks a lot. Bye.